So good afternoon to all, and myself Y. Harnath, Assistant Professor in Anantalakshmi Institute of Technology and Sciences. Today, as a part of Advanced Data Structure and Algorithm subject, today we will discuss about the asymptotic notations. So asymptotic notations. So normally asymptotic notations are mathematical notations normally that are used to describe the running time of an algorithm. Suppose if you are going to give if you are take any algorithm, so how much time required for the algorithm to complete those things. So when input tends towards particular value or limit of the value. So in asymptotic notations, we represent the complexity with the most significant terms. Normally we'll use the most significant only in order to represent the asymptotic notations. So we mainly will ignore the least significant terms of the complexity of algorithm. So suppose let's take an example of suppose 5n square plus 2n plus 1. So in this is the time complexity of two algorithms, algorithm 1, and suppose I am taking here two algorithms. One is 5n square plus 2n plus 1. So in this algorithm, how you are going to represent this algorithm? Note. So the most frequent term will be taken. What is the most frequent term here? So 5n square, n square plus 2n plus 1. So n square is the most significant term, but if 5 is the constant, we can skip it easily. So we'll have only the n square. So in order to represent the time complexity of an algorithm, so here we'll use the 5 types of notations: big O notation, big omega notation, theta notation, little o notation, little omega notation. So these are the 5 notations we'll use. So what is the first one? Big O notation. So normally the big O notation is used to represent upper bound of an algorithm. So in terms of the time complexity, it takes maximum time. So it takes maximum time to complete to give the output. So we can treat it as a worst case of an algorithm. So a worst case of an algorithm time complexity, we can represent this as by using the worst case. So big O represents the worst case of an algorithm. It takes the maximum time required by an algorithm for the all inputs. So how you are going to notate this defined can be defined. Very important here, I am taking two things. One is f of n is the actual time complexity of the algorithm, and g of n is the most significant term for this algorithm. So for this one, f of n must be less than or equal to c into g of n. Here, so f of n must be less than or equal to c into g of n, because it takes maximum time. So as the inputs increases here, it takes the maximum time than the f of n. So it can be considered worst case of the algorithm. So that's why f of n less than or equal to c into g of n. So for all n greater than n0, c greater than 0, n not greater than equal to 0. So we can represent as f of n as big O of g of n. Big O of g of n. So let's take this graph already discussed about this. So if the number of inputs increases, how the time will act? Though f of n is the time complexity of an algorithm, but the most significant term for this one is c into g of n, which is actually maximum than the required one. So it is worst case of an algorithm. It takes maximum time. Okay. Next, big omega notation. So big omega notation is used to define lower bound of them, and it takes less running time to bound this algorithm. So omega represents lower bound of the running time of an algorithm. Thus it provides best case time complexity of an algorithm. So we can treat it as a best case, whereas big O is treated as a worst case of an algorithm. Now this omega will treat it as a best case of an algorithm. So how we are going to define this one? So same as the previous big O notation, consider f of n as the time complexity of an algorithm, then g of n is the most significant term. Here f of n must be greater than or equal to c into g of n. That means, so what is the actual time required for this one, actual time complexity of f of n? But c into g of n, which takes less time when compared to the f of n, so it is a best case time complexity of an algorithm. So that's why we are going to use the notations in order to represent the time complexity of an algorithm. In case of it may be a mainly three cases will deal with here: best case, worst case, and average case. So already we discussed that worst case is nothing but we are representing by using the big O notation. In order to represent the best case time complexity of an algorithm, will use the big omega notation. So that's why here in x-axis we am taking the number of inputs and y-axis I am taking the time. So if the inputs are goes on increasing, then what's the time required for this one? If the number of inputs increases, how much time it required to complete? So normally f of n is the time complexity of an algorithm, but c of n is taking less time when compared to the f of n, so it is a best case of an algorithm. So next, big theta notation. So this theta notation mainly describes average case scenarios. We already know that. So it may be take maximum time or it may be a take less time to complete those things. So in realistic time complexity, every time algorithm does not. Normally we can say that. So any time algorithm performs, it doesn't give the same result. So it may be a worst or best. In some cases it may give worst. In some cases it may be a gives best. So every time an algorithm does not perform worst or best. So normally, so it fluctuates between best and worst case. So that's we can treat as a average case of an algorithm. Average case on algorithm. So it is mainly used for worst case as well as best case. So we can represent it as both upper bound and lower bound. It has both upper bound and lower bound of running time. So let's take the we can define as where f of n is the time complexity of an algorithm and g of n is the most significant term. Now, so here if c1 g of n less than or equal to f of n, that is this is the best case, and f of n is less than or equal to c into g of n. So which is less than means c into g of n, which is less than f of n. So this is the worst case of an algorithm. So here I am by using the mathematical representation. Here I am representing both best case as well as the worst case. So we can represent it as f of n as theta of z of n. Theta of z of n. The same way here, the x-axis will have inputs and y-axis will have a time. If the number of inputs increases, the time what's the time you are taking when the number of cases are increasing. So this graph indicates the big theta notation, that is nothing but average case time complexity of an algorithm. Next, little o and little omega. So these are fully different than the big O. Big O normally we can treat it as tight upper bound. So growth of an algorithm effect, it must be a tight, it can't be a loose. So it must be a tight upper bound. Whereas little o, it may be a tight, more clear. Little o notation describes upper bound that can't be tight. Sometimes it may be a loose. So that can't be tight. Same as little omega also. So it is a tight lower bound. Tight big O is a big omega is a tight upper bound, whereas little omega is a loose lower bound. Loose lower bound. It may be a, sometimes it may tie upper or lower. So we can't justify this one. Okay. So that's our this is the overall graph representing the different algorithms of your things. So initially this is a graph. If you are having here, the x-axis will have the number of inputs and y-axis will have the time taken for this one. So where f of n is the main time complex function complexity of an algorithm, so then omega we already know that, so omega theta, big O, small omega, all these can be represented by using this graphically. So more precisely, next class will take an algorithm and will deal with how you are going to calculate these algorithms. Okay, thank you.